This is Linrad running on a Supermicro X9DAi with two processors, each one having 4 CPU cores. Hyperthreading is disabled. With hyperthreading, the system doesn't work properly. Linrad is running at 100 MHz bandwidth, that is 200 MHz sampling speed. Processing is set for optimum performance, and the CPU load is very high. You can see about 90% in 1, 2, 3, 4, 5, 6, 7 of the CPU cores. And then there is some load, 20% here, and some small percentages on other threads. The total load is 83%, and the task manager of Windows is in agreement on that. And you can see the load is high in 7 cores and a little bit above 50% in one of the cores. There are very few glitches. There was one here, and you can see it in the baseband graph here. I will now change the antenna. This is a crystal oscillator, very high level, 1 dB below saturation. That is to make glitches extra visible. Now there is an antenna, and since this is FM mode, I should click on an FM station. This is the strongest one at the moment. And the appropriate bandwidth is like this for an FM station. And this works flawlessly, very nice. But Windows 7 has a peculiar behavior, and that is what this video is about. I can reduce the CPU load, and I do it in 2 steps. Firstly, I will reduce the amount of computation of average power spectra. That will affect this thread. And I do that simply by making the displayed spectrum width smaller. Can do this in steps. And you can see it doesn't respond as quickly now when the load is lower. It's down at 32%. Where did we have it here? 30%, 28%. I go like that. And you see there is a problem coming at regular intervals. And this is because the load is now uneven. I think the explanation is that all processors no longer run at full processing speed. And I will show some experiments that indicate that this really is the case. And for that purpose, I will connect a sweep generator to the input of the AD converter. And I will restore the glitch-free operation by clicking here to display the full bandwidth. Like this, and display faster, let's say 10 times faster, like this. This is the sweeping signal with aliases going the other way and overtones and things. And this runs now without glitches. So sweep starts at 1 MHz and it goes up to 99 MHz. I can record this by pressing S, and I call the file X just, and now Linrad is recording. We had a glitch there, so I will stop. And I will make the risk of glitches a little bit smaller by going to the parameter and allowing one more thread for the bulk of FFT. I go from 5 to 6. And here you can see recording of the sweep signals. And I will again press S and name the file X. It will overwrite any old file with the same name. You can see drawing the waterfall had some little things. It doesn't have highest priority, but there is a file being saved now, and I stop recording and escape and X, and now process the first file. I have set that up to show the file x.raw in the Linrad data directory. So I press 2. Oops, that was not right. I should have pressed 1 because this is a raw file and I want it in FM mode, and I don't want to repeat it. And here you can see the recorded file at 200 MHz sampling frequency, 16-bit data. It records for some time, and then suddenly you can see it doesn't work. And this was the entire file. This computer has 64 gigabytes of memory, and when recording to the hard disk, Windows 7 is clever enough to use very big buffers. But at some point, that's up here, buffers are not big enough and we are losing data. And recording to the hard disk is, you can see on the slope how much slower it is, roughly. The purpose of showing that I can record over a time of about from 45 to 55, that's 10 seconds, say 15 seconds nearly goes into the buffering before recording fails. That will be useful a little bit later in this video when I show how errors behave. I have now connected another sweep generator, sweeping from 2 to a little bit above 3 MHz. The display is only 18 MHz, but there are no glitches now because I have still 6 threads for the bulk of the FFT. The 6th thread that I enabled before. I can save for a while, press S and then X to overwrite the old X file, and it's now 5 seconds, 10 seconds, 15 seconds, 20 seconds about. Stop, X and X, and I will look at that. It is 1 and E and no, and here comes the recording. And you can see recording is successful for a while. And here the recording fails. And you can see that the recorded data is maybe 25% of the total data, something of that order. So recording can be done at 25 MHz bandwidth or so for a longer period of time. This was to demonstrate that the recording does not add any particular error. So I go back, X, X and E, and now I will change the parameters to get back the glitches that are typical when the load is very uneven. So that is X, P, and I set this to 5. And look at the load. You can see here are glitches, and there and there. They repeat quite frequently. And what happens is that data is lost. And it's lost in a peculiar way. I will look a little bit into details on that later. Interesting is that I can record this, and if you look at what happens, I say S and then X, and when I press enter, recording will start. And it started here, and I will do 1 cycle and a second cycle, and then I stop. And then X, X, look at this, and E, and no. And what we see here is exactly the same that we saw while doing the recording. This means that loss of data is in the input to Linrad. It's not in the transfer between different processing stages. And Linrad is writing from the first buffer into which the callback routine puts its data. And I can use the recording and look more in detail what is happening. That was a little bit too far. X, B. Here we have, I can run it faster, let's say 30. And then again X, B. And I have forgotten the commands. I have to look. Shift F3 was the command I was looking for. 1E. No. Shift F3. Here. So something very odd happens. Some blocks of data is fetched at the right time all the way up here, and some data is corresponding to a later time. This point should have been up here. Buffers are relatively small, so this is some odd phenomenon within the PCIe bus, I think. But the pattern depends on the buffer sizes. So it is related to the organization of memory and far beyond what I can know. I am now a little bit closer. Maybe this is related to how information is moved to the cache of the CPU. It could be something else, but the size of data blocks that are on the wrong place do not fit to the size of data blocks within Linrad. It's something else.